Let's talk about Newton's third law. Newton's third law gets said many different ways. The way that I've worded it here, I'm hoping will help avoid some of the misconceptions that come up with it. I said for every force on an object, there is an equal and opposite force exerted by the object. And that says right there what I'm hoping one of the big takeaways you have from this video is that if we're talking about force pairs, it's always acting on two different objects. There's the object that's being pushed on, and the force pair is it pushing back on something else. So to illustrate that, let's do a quick, simple problem where we just have, in fact, let's just go back to that apple that I had sitting on a table actually, it was sitting on a book or something, but whatever. Yeah, we'll just put that apple on the table and let's draw the free body diagram for it. Here's my apple, here's my table. So on the apple, we have two forces. We're going to have the force of gravity acting downwards, and we're going to have the normal force acting from the table. And I'm going to go back and add all those labels that we've been doing for a while because this is where they're going to come in handy. We have a contact force acting on the apple by the table. And then we have a field force acting on the apple by the table, or I'm sorry, by the earth. Okay, these can't be a Newton's third law pair. They are, in this case, equal in magnitude and opposite in direction. But there's no law that says that they have to be. We could create scenarios in which that apple has more normal force or less normal force if we wanted to. For example, if I put my hand on top of that apple and started pushing it down as hard as I could, suddenly the normal force from the table is going to go up and up and up and up to match me pushing it down. And now the normal force from the table and the force of gravity are nowhere close to the same. So these are not a normal Newton's pair. And I'm going to kind of just like that and that. That's a big no. That's a common no, but it's a big one. Now let's talk about the table. The table has, we'll say the table's a little bit heavier than the apple is. So there's mg there. The table also has okay, so that's mg. We'll do all the red stuff. Okay, it's a field force on the table by the earth. The table's also being pushed downwards by the apple. You guys, maybe you can't tell that that's happening when you look at the apple on the table, but if I put the apple on your hand, you'd be able to tell, oh, the apple's definitely pushing down on me. I can feel it in my hand. You're not feeling the force of gravity, you're feeling the apple pushing on your hand, which indirectly is because of the force of gravity, but you feel the normal force of the apple, and so does this table. It's equal and opposite in magnitude, though. There it is right there. You can see, oops, it should be, I guess, a little bit longer. You can see that it's going the opposite direction. And if I write out all of the little red stuff on here, this is a contact force. It's acting on the table by the apple. And if you can swap these two words, table, apple, apple, table, then it's a Newton's pair. If you can't swap those two words, it's not a Newton's pair. It has a pair somewhere, it's just not in that location. So here we have apple, table, apple, earth. Those aren't a Newton's pair because they're acting on the same object, they're different forces, and the words aren't flipping. These ones here, this one and this one, that is our good Newton's pair. And then there's one more force acting on it. There'd be a big force acting upwards, and that's a new normal force, but that's the normal force, again, contact on the table by the ground. But that's a separate force. I could draw more free forces. I could draw the free body diagram for the ground, and then we would find the Newton's pair for this, because there's a contact force on the ground by the table. I could draw the earth itself, and we would find the Newton's pair for these two. We would find the field force on the earth from the apple pulling on it, and the field force on the earth from the table pulling on it. And we'll talk about that particular action-reaction pair in a later lesson, but every force has an equal and opposite reaction. So I have an example problem right here. And this example problem shows a really great way to use Newton's third law to start solving some problems. I'm going to draw free body diagrams for each one of these objects. And what we want to do, we have M1, M2, M3. We're just trying to find what the magnitudes of the normal forces are acting on each one of these. I'm going to do this without drawing force equations. I'm going to do this just with free body diagrams and show you how useful Newton's third law can be. So for M1, we're going to have the force of gravity pulling down on here. We know that that's mg, and since m is 2 kilograms and g is 10, this would have to be 20 newtons. That's 2 times 10. 2 kilograms, 10 meters per second per second. So it's 20 newtons down. Now we know this is not a Newton's third law pair, but we know that because mass 1 is in equilibrium, it's not moving, that normal force has to be exactly the same. So we have normal force here. This is the normal force on 1 from 2 is equal to 20 newtons. That means we can now go to here, because now we can say the normal force on 2 from 1 has to also be 20 newtons. But it also has the force of gravity, mg, which is 20 newtons. So we have 20 newtons down from the action-reaction pair of the normal force here, 20 there, which means we must have a net of 40 upwards, and that is the normal force on 2 from 3. Then for mass 3, we can draw that one in right away. There it is. There's the normal force on 3 from 2. They have to have the same magnitudes, which means we know that this is 40 newtons. We know that there's the force of gravity acting on it, which is equal to 20 newtons, which means now we can figure out that the normal force upwards has to be equal to 60 newtons, and that is the normal force from the table, or whatever the surface is, the table. I'm sorry, I'm keeping this consistent. That's the normal force on 3 from the table. So our normal forces are 20, 40, and 60, depending on whether we're talking about the contact force between 1 and 2, the contact force between 2 and 3, or the contact force between 3 and the table. So that's how you would use Newton's third law to solve some problems. And we have one more example problem where I'll show you some other applications of it. Thanks for watching.